Welcome to Episode 32, Peering, DNS, and Name Resolution, where we explain how networks connect and how names reliably point to the right places. Applications rarely live in one private island. They span environments, regions, and even clouds, so links and lookups must be intentional rather than improvised. When connectivity is clear, services talk with low latency and predictable security boundaries. When it is fuzzy, teams chase intermittent failures that look like bugs but are actually path or name issues. The purpose of this episode is to turn connectivity and naming into simple, repeatable design choices. We will move from private backbone links to hybrid name resolution, always asking why a step matters in practice. By the end, you will be able to connect, resolve, and operate with confidence. Virtual network peering creates private backbone links between Azure virtual networks so traffic flows as if the networks were one fabric. Peering is non-overlay and high bandwidth, which means no extra gateways are required and latency remains low. The link is encrypted on Microsoft's backbone and inherits each network's security rules. A small scenario helps. An application tier in one network calls a database in another without touching the public internet, improving performance and compliance posture. A misconception is that peering changes address spaces. It does not, so good planning still matters. Practical setup is symmetric. Create peering in both directions and verify effective routes and security rules. With that, services discover each other privately and predictably. There are two common shapes of peering to consider: regional peering and global peering. Regional peering stitches networks within the same region and is often used for hub and spoke layouts. Global peering connects networks across regions with the same operational simplicity, though costs and latency reflect distance. Choosing between them comes down to user proximity, data gravity, and resilience expectations. For example, a global e-commerce platform may run front ends close to users and centralize shared services in another region, then bind them with global peering. A misconception is that global peering replaces disaster recovery planning. It only provides a path, not state or failover logic. Measure latency and plan replication accordingly. Peering is powerful but intentionally limited. It does not provide transitive routing. Traffic can traverse from network A to network B and from network B to network C, but it cannot flow from A to C through B unless you deliberately place and route through a device that supports it. This matters because real environments grow into meshes unless you keep paths intentional. Consider a shared security hub. Spokes peer to the hub, but you still must design routes so traffic passes through inspection points rather than accidentally bypassing them. A common misconception is that adding one more peering makes everything reachable. It might create black holes instead. The remedy is a hub and spoke pattern with explicit next hops. Gateway transit extends a peered design by letting a spoke network use the hub's gateway for connectivity beyond Azure. You enable the hub to advertise its virtual private network or private circuit routes and the spoke to use them. This concentrates egress and inspection in one place, simplifying operations and audits. A practical example is a single express route or virtual private network gateway in the hub serving many workloads. The misconception is that gateway transit is automatic. It requires configuration on both sides and aligned route tables. You still apply network security groups and firewalls to shape flows. When configured well, gateway transit prevents a sprawl of gateways and keeps hybrid paths consistent. Domain Name System, or DNS, underpins how services find each other, and it comes in two broad scopes: public and private. Public DNS hosts names the world should reach, such as product sites and public application programming interfaces. Private DNS serves names only resolvable inside one or more connected networks. This distinction matters because many Azure services can exist privately even though they also have public counterparts. A simple scenario helps. User browsers resolve a public name, while internal services resolve private names that stay off the internet. A misconception is mixing both in a single zone without clear intent. Keep scopes distinct so audits and troubleshooting remain straightforward. Azure DNS zones and records provide authoritative answers for chosen domains. Public zones host records like A, CNAME, and TXT for external clients, while private zones host the same record types for internal resolution. Consistent naming conventions signal environment and region so automation can select the right target without special cases. For example, app prod east can map to one address today and a different address after a blue-green swap, while clients continue to use the same name. A misconception is relying on host files or hard-coded addresses in code. That blocks agility. Treat zones as infrastructure, version changes, and propagate them through pipelines. Private DNS zones pair naturally with private endpoints, so platform services resolve to private addresses inside your networks. When a storage account, database, or message broker uses a private endpoint, its public name resolves to an internal address for clients in linked networks. This reduces exposure and satisfies strict data path requirements. A scenario: an application server calls a database through a private address, even though the database is a managed service. The misconception is assuming the mapping happens automatically for every network. You must link the private zone to the networks that need resolution. Verify with name queries from actual hosts, not just from your workstation. Split horizon and conditional forwarder strategies let the same name resolve differently for internal and external clients. Split horizon means internal lookups receive private answers, while external lookups receive public answers, preserving a single brand name with two realities. Conditional forwarders send queries for specific zones to authoritative resolvers, which is essential when multiple teams or companies own different parts of the namespace. A practical example is forwarding all corp.internal queries to on-premises, while cloud zones resolve natively in Azure. A misconception is that forwarders fix slow name resolution by default. Performance still depends on network paths and resolver health. Monitor response times and cache behaviors to keep logins and app calls snappy. Hybrid name resolution through gateways ties on-premises name services to cloud name services so applications can discover each other across the boundary. Virtual private network and private circuit links carry the queries, while conditional forwarding ensures each side answers for its domain. This matters during migrations when workloads move in phases but must still interoperate. Picture a payroll system in Azure calling an on-premises identity provider by name and the reverse for callbacks. The misconception is treating DNS as an afterthought once tunnels come up. Unresolved names look like application bugs. Document authoritative zones, forward rules, and fallback resolvers, and test failover deliberately. Multi-virtual network naming design patterns aim for clarity under growth. One approach centralizes private zones in a hub and links SPOS for consistent records, while another approach delegates per application zones to teams with clear prefixes. The right fit depends on autonomy versus consistency. A retail example might centralize shared platform names while delegating microservice subzones to product squads. The misconception is that one global zone solves everything. It can bottleneck changes and create coupling. Whatever pattern you choose, publish conventions, automate validation, and ensure every new network links to the zones it must see before workloads deploy. Troubleshooting peering and DNS failures follows a steady, layered method. First, verify addresses do not overlap and that peering exists in both directions with the right permissions. Next, confirm effective routes on each network interface and ensure network security groups allow the intended ports. Then, test raw connectivity with simple tools, and only after that, test name resolution with fully qualified names. For DNS, query the exact resolver the host uses and trace delegation from zone to record. A misconception is jumping straight to code changes. Most issues are path, rule, or record related. Write down each finding so the root cause becomes a fixable design lesson. Connecting networks and resolving names are everyday operations, yet they decide whether apps feel instant or fragile. Peering supplies private paths. Gateway transit extends them to hybrid. And unique address plans keep growth painless. Public and private DNS give you separate but cooperating views of the world, while private zones and endpoints bring managed services inside your boundary. Split horizon and conditional forwarding keep names consistent for users and systems. When problems appear, a calm checklist translates mystery into measurement. With these habits, you connect, resolve, and operate confidently, turning a complex map into a dependable platform your applications can trust.